Okay, let's take a look at another question regarding beams, and this one is going to be indicating shear force again, the same as the last video that I just posted. Okay, so the reference for this question is going to be self-test problem number 9 on page 29 of chapter 6 of your 3A1 textbook. So the question reads, a beam is 14 meters long and has a uniformly distributed load of 60 kilonewtons per meter in the middle 10 meters of the beam. A point load of 200 kilonewtons rests on the left end of the beam, and a point load of 300 kilonewtons is located at 4 meters from the right end. If the supports are located at 2 meters from each end of the beam, find the shear force at the center of the beam. And according to the textbook, the answer is 100 kilonewtons. So let's see if we can work this out and agree with that number. Okay, once again, I've gone ahead and taken the liberty of sketching up my diagram for this arrangement. So we can see here it's a simply supported overhung beam, and what I've got here is my reaction forces indicated by my sort of upwards down triangles here of R1 and R2. Now in this question, I know what my point loads are, I know what my distributed load is, but the problem is I don't know what R1 and R2 are. So that's where I've got to start and actually calculate that. So this is a great question because we get to practice calculating reaction forces as well as practicing the shear force to actually get the final solution to this question. Alright, so let's start off and get our reaction forces. First of all, we're going to have to decide which side of XX that we want to go with, to the left or to the right. As our section XX is down in the middle, it doesn't particularly make much of a difference because we have a point load on both sides of XX. So it doesn't really matter whether you would go for R1 or R2. I'm going to analyse this from the left-hand end, as that's usually how I start all reaction type questions with regards to beams. So first of all, let's write our statement down and let's take our moment about R1. Okay, so if we take our moment about R1, we now can say then that our clockwise moments must equal anti-clockwise moments if we are trying to get equilibrium, which of course is what we're solving for. So with regards to this then, starting over here, my fulcrum is going to be here at R1, which again, fulcrum is just a fancy word for the pivot point. Now in this example then, I want to look from R1 and pick up all my forces that are going clockwise. So working from the left-hand end, my 200 kilonewtons at R1 would be acting in an anti-clockwise direction. So I can skip over that one as I'm only interested in clockwise ones at the moment. Looking to the right of R1, we now get our distributed load. Now, our distributed load would also be acting downward, and in this case, it would be acting in a clockwise direction. So I need to pick this one up. Now, we can see on my diagram that the bumpy line is in between the R1 and the R2. Now, the entire beam is 14 meters long, and we have R1 2 meters here from the left and R2 2 meters here from the right. That then means that the distance in between R1 and R2 is 10 meters. That is 14 minus the 2 at the right hand end and minus the 2 on the left hand end, giving us that 10 meters. Now the load over that is going to be 60 kilonewtons per meter over our 10 meters. So we can work that one out then and multiply the force out by the distance, which is going to be my 60 kilonewtons per meter, multiply it by the distance that it's over, that is 10 meters that we found from the diagram, but now we've got to multiply it by our distance from the center of the section back to R1. Now what I mean by that is that the distributed load is over a 10 meter section, or in the middle 10 meters of the beam. So if I split the difference on that section, it would be 5 meters to the right of R1 to get to the center point of the distributed load, which of course is the dead center of the beam. So I can replace my distributed load of 60 kilonewtons per meter over my 10 meters, and I can simply replace it as a point load here dead centre of my beam, or if you prefer to describe it as 5 metres to the right of R1, and call that my 60 multiplied by 10, which gives me my 600 kilonewtons. So my distance, 5 metres, and that now completes that first part. So let me just go over that again. We've got our 60 here because it's 60 kilonewtons per metre. My 10 is because the uniformly distributed load is over 10 metres of my beam. And then the 5 in this is because the centre of that uniformly distributed section is 5 metres from R1. And remembering, when calculating moments, we always have to go back to the fulcrum. So that's my first load to the right of R1 going clockwise. We can now pick up my next clockwise moment moving to the right, and this one's going to be my 300 kilonewton. So we multiply out now, we have our force, 300 kilonewtons, multiplied by my distance from R1. Well, looking at my diagram, I've got 4 metres of 300 kilonewtons in from the right hand end, and my R1 is 2 metres in from the left hand end. So that now basically is going to give us a distance here of 8 metres in between R1 and the 300 kilonewtons. How did I end up with that? Well, I took my total distance of 14, I subtracted 2 off of it to get to R1, then subtracted another 4 off of it to get my 300. That gets me 8 metres. Those are all my clockwise moments complete. Let's now take a look at the anti-clockwise moments. So moving to the right of my equation then, my first anti-clockwise moment is going back to the left-hand end of the beam, and that's my 200 kilonewtons. So 200 kilonewtons multiplied by the distance from the 200 to the R1. This one's more straightforward because we can see on the diagram it's just 2 metres. We can now add that to our next one, which is going to be my R2. Now, I don't know what the R2 force is, so I can just keep calling it R2 and now multiply it by the distance back to R1. Well, this is going to be a distance that we talked about earlier, that being 10 metres from R2 to R1. That there then is our great big equation that we can now start to simplify down. So let's do that. Well, 60 times 10 is 600, and 600 times 5 gives me 3,000. 300 times 8 gives me 2,400. 200 times 2 gives me 400, and R2 times 10 gives me 10 R2. We can simplify this. 3,000 plus 2,400 is 5,400. And on the right-hand side, that can stay as it is, 400 plus 10 R2. We can now go ahead and transpose this to finally get it. So that means R2 is going to be equal to the 5,400 minus the 400 by taking my 400 over this side. Remember, it's plus over here, so it's negative over here. And then the last one we've got to do is we've got to take that 10 over as well. Well, it's a times over here, so it's a divide over there. So I can pick that up in my final equation here as divide by the 10. So this is going to give us 5,400 minus 400, which is our 5,000, and then 5,000 divided by 10, which gives us 500 kilonewtons. And there is my first reaction force. Now, if I was just looking for the shear force here and I was going to the right, I wouldn't actually have to work out R1. However, because this is just a practice run, we're going to calculate it for the sheer joy and practice of it. So to calculate R1, I'm going to say that the upwards forces equal the downwards forces, because this is one of our laws of equilibrium. Remembering that our laws of equilibrium are clockwise moments equal anti-clockwise moments, upwards forces equal downwards forces, and leftwards forces equal rightwards forces. Well, to get my upwards forces, I just have to look back up at my diagram, i.e. up here, which hopefully you've drawn out by now, and work out which ones are the upward forces. Well, the upward forces are R1 and R2. So let's put them in. Now we don't know what R1 is because we haven't found it yet, but we did just work out what R2 is, and that was 500 kilonewtons. So those are all my upward forces. My downward forces now are all the loads on top of the beam pointing downwards. So that's my 200, my 600, and my 300 kilonewtons respectively. So on the right-hand side of my equation, that's going to be 200 plus my 600 plus my 300. We can simplify this down as 200 plus 600 is 800, and 800 plus 300 is 1100. We can now find the answer out that R1 would be equal to 1100 minus 500, because once again, if we take that 500 over there, it goes from our plus sign here to a negative sign over here. So 1100 minus 500 gives me an R1 reaction force of 600 kilonewtons. So now then, we've got both of our reaction forces of 500 and 600 kilonewtons respectively. Now I've got that, I can actually finally get on to working out the shear force in my beam. So, looking back up at my diagram here, we can see that section XX, dead center, is going to be the point at where I'm going to look for my shear force. So what I'm going to do with this is basically look to the right or the left. Now, we've got to pick one of which way we're going to go with this, and so what we'll do is we're going to just arbitrarily choose the shear force to the right. As I said earlier, it doesn't really make a difference if you go left or right with this one because the shear force is in the center. But to keep it sort of consistent, we'll go shear force to the right. So let's do that. Let's just zoom out here. So shear force going to the right hand side. Now remembering, downwards forces are negative and upwards forces are positive. Well, if we look to the right of section XX, the first force we come to is that 300 kilonewtons, and it's acting downward, which means it's positive. The next force that we get if we look to the right is our R2, but that's actually acting upward. And we found R2 earlier was equal to 500 kilonewtons. So I've got to give that a negative sign again because it's going upward, meaning negative. Now the last one we've got to pick up is the distributed load section to the right of section XX. Now looking back at my diagram here, we can see that on this diagram, to the right of section XX, or the dead center of the beam, we've got to find out how long this distributed load section is right there. Well, the whole distributed load section is over 10 meters between R1 and R2. So that means our uniformly distributed load to the right of XX is half of that, which is 5 meters. So our load of 60 kilonewtons per meter is acting over 5 meters. So if we multiply that out, we will get our load acting downward for our uniformly distributed load. So let's take a look at that back in our solution. Okay, so we're going to add it because it's acting downwards. We have 60 kilonewtons per meter, and to the right of XX, there is only 5 meters of that uniformly distributed section. So, simplifying this down, 300 minus 500 is minus 200, plus 60 times 5, which is 300. That now gives me minus 200 plus 300 gives me plus 100 kilonewtons for my shear force to the right of section XX. Now let's look back at the diagram here and see once again what that means. Well, to the right of my section XX, because I has a positive sign, it means my shear force to the right is acting downward, which must mean to the left of XX, my shear force is acting upward. So that's the answer to this one, 100 kilonewtons acting downward to the right or acting upward to the left of section XX. Hope this one helped, and that sort of sets you a little bit more comfortable with regards to shear force calculations. So I'll see you in another video. That's it for this one.